Thank you very much for the introduction and the invitation by the SEC Planning Commission. So I wanted to address this issue of variability with photovoltaic energy. My research lab, the Renewable Energy and Advanced Power Electronics Research Lab, one of its missions is to promote the increased utilization of photovoltaic energy systems. Now, we don't make the cells, but we do everything that interfaces the cell level to the grid level, so cells to grid. So I wanted to start off by telling you a little bit about how we accomplish that mission, and that's through our teaching, research, and public outreach. So many universities have PV arrays. I think the way we did ours is a little bit unique. It's DOE funded and also administered by the Texas State Energy Conservation Office. It was really brought to fruition through a unique partnership between athletics, faculty, facilities, and our alumni network who did the installation. The actual system is, which you can see an aerial shot of, represents somewhere between 5 and 10 residential homes. So depending on if it's a 2 to 5 kilowatt residential system. It was purposely chosen, the location on campus, to be within plain view of 83,000 game day spectators. So we've tapped a target audience that might not normally be inquisitive about photovoltaics. We call that the accidental learning opportunity, because partnering with the athletics department during plays and pauses in the game, we put 15-second video clips on the Jumbotron. So we could, the community outreach, we could tap a large segment of the population and really show them the science behind photovoltaics. On the teaching and research side, the data that we're collecting from the system, we use in our classes. So for teaching, we analyze that data, and we also use that in the research. And some of the results shown today, the underlying data came from that campus array. So we can't really talk about solar without talking about apple pie and motherhood. Who could say anything bad about those things? Well, the sun is the single most abundant form of energy on the Earth. And the 150,000 terawatt hours of power that reach the Earth every year is equivalent to 6,000 Earths if you project our energy consumption out to 2035. So certainly, if we could tap even a fraction of that, we've got our problem solved. However, we're not there yet. Nowhere even close. And a lot of the issues come from non-cell issues. Now, if we think about sunlight, it's the most highly distributed form of energy as well, and something that we don't take advantage of yet currently. And so the system that we'll be examining in this presentation adopts the concept of millions and millions of rooftop solar arrays, as opposed to smaller concentrated solar arrays or utility scale solar arrays. Now, despite the fact that that there's plenty of it and it's widespread, we actually use about less than 1% of our electrical generation comes from solar energy or a direct photon to electron conversion. That's not because of lack of investigation on the material science side, which has been going on for 4 decades now, but we see non-cell challenges are key. And so a thesis statement is that if solar cells were free, we still couldn't afford photovoltaic energy. And one of them is this concept of mitigation of the variability. So what is this variability? Well, there's this high penetration perception that once we have too much solar on the grid, it's going to cause instabilities, voltage swings, frequency swings, and basically widespread blackout. Well, let's contrast that with the fact that Germany has over 30% penetration of PV and set a world record in May 25th of last year, generating 22.4 gigawatts. That was a world record for PV. That put their penetration at about 37%. And I'm glad to report their grid did not go unstable. There were no widespread blackouts and no looting in the streets. So let's look at a concept where we have a high penetration of solar. And so on a conventional distribution system, so this is down at the load side, none of the high-level T and D in the power systems, but we have a radial distribution system where power traditionally flows from the grid down into all the loads. And now we start putting PV on all of these residential homes. And of course, the sun is variable. There's cloud coverage that comes in, and so we have some variability. And perhaps if it was only one home in the neighborhood, it might not be as significant. But when we aggregate all of these, and if they're geographically in proximity, there's a high correlation between the variability. The net effect, as seen by the utility, ends up being, well, let's see, if this line is the constant load, and the green is the variability of the solar, we end up having this red line, which is sometimes acting as a load and sometimes acting as a generation. So this is the bad scenario, where what used to be just a load can sometimes be a generator. And the utility has no control over this. So let's compare that to a concept where we have a community-based microgrid. So we have a high penetration scenario. We take this community and we'll put this on a microgrid. We'll add some community storage. Now, we can't mitigate Mother Nature, so we have to somehow deal with this variability. We'll do that with a community-based storage. So not a utility scale, multi-megawatt hour, but something that would look like a pad-mounted transformer in your neighborhood. We interface that with power electronics back into the existing distribution system. And our question is, can we do better? And so I want to focus on three different areas. The first is the temporal resolution of our planning data, and more specifically, hourly data versus sub-hourly or 10-second data. I want to look at the concept of what the community storage as a shared resource can do for the system, and then look at some non-traditional photovoltaic array geometries. Now, I might preface the next series of slides by, when I started talking about this in my class on renewable energy, power electronics for renewable energy, I had a student who interned last summer for a major utility up in the Northeast. The point of his internship project was to cook up scenarios in which a high penetration of PV would cause instability in the grid. Not for the purpose of mitigating that, but for the purpose of taking those scenarios to the PUC, the Public Utility Commission, to prove to them that solar was bad and would cause collapse of the power system in New York and New Jersey, kind of like we saw in 2003 and we continue to see every time there's a snowstorm. So the first thing that we wanted to look at is what does this system look like? How does it behave, or how do we think it behaves if we have hourly data? So hourly data is what's available from the NREL data sites. It's the resolution of the data that's commonly used for planning purposes. So we see if we plot a histogram, so we have the number of hours and then the import or export event. So when we're importing power, this is when the load is consuming more electricity than the PV can produce. And the variability of the sunshine means that we actually import a variable amount of power. So from the utility's perspective, this is a completely uncontrollable load. And yet they're required statutorily to maintain voltage regulation and frequency regulation over this range. Every once in a while, when there's enough generation from the PV and the community becomes a net exporter, we see that we actually fall into this category where we could actually operate the system as a controlled source. So take all the work that's been done in the smart grid with the communications advances. The utility can now negotiate with the power electronics, the inverters, and the PV systems to control or throttle the amount of this power that's injected into the system. So this variability is what we're trying to address. If we look at the same system, the same geographic location, and instead look at the high temporal rate data, we see something really interesting. We see a decrease in variability. So we see that the frequency, so the height of these decreases, and the intensity, we move closer to the net zero line. So the exact same scenario, just looking at the temporal resolution, suggests that the variability may not be as great as the utilities or the naysayers suggest that it is. We still do have some variability, however, so what can we do to help further mitigate that? So if we look at a traditional system, and this is a different set of data, again, taken from the campus PV. So this is real data, not models from IEEE or EPRI. We see that for a given period of time, this is about 3 days worth of data, we sometimes operate as a variable controlled source. So this is the good scenario, and this is the undesirable scenario. If we add storage into the system, so this is community level storage, we could further decrease this variability while increasing this controllability. Now you might say, well, what's the advantage of a community scale storage instead of a grid level storage? Well, the idea is that the closer you could mitigate to where the load is consuming, the less power flow we have back into the system. So the less losses of the system, the less bidirectional power that flows from the point of load all the way up through the distribution system and then back into the transmission system. So we're alleviating congestion on the system by mitigating this variability where it occurs. Somehow, there's a slide that is missing. Okay. So we talked about the temporal resolution of data. We talked about the storage. What we could also do is a third concept of non-traditional, or what I call non-planar. So a lot of advances in the material science of the solar cells means that we're not locked into the rigid flat form factor of the PV arrays that are currently being marketed. And so if we consider that a future solar active material can be laminated to any type of roofing material. So in many parts of the world, we have these terracotta roof tiles, semi-cylinder geometries. What that allows us to do is to really changes the profile of the energy capture. So in mechanical engineering, we'd call this the view factor geometry of the system. The direct beam radiation from the sun has the greatest intensity, and so that's why in traditional PV systems we use tracking. If you could keep the surface normal pointed directly at the sun, you've maximized the harvest. When a system like this, regardless of the position of the sun in the sky, we have a portion of that array that's directly normal to the sun. So we could increase the energy harvest without needing to increase the real estate of the rooftop. So same footprint on the roof, greater energy harvest over a wider range of the day. So we flattened that energy generation curve over the course of the day of the PV. When we combine this type of strategy with the small-scale community storage and the high temporal resolution, we can actually see that we have the ability to completely eliminate this variability. So we took a system that was a mix of PV in a high penetration scenario and load, and we've flipped it so it behaves completely as a controllable generation. Now, this allows the utility to completely control how that community, that smart grid-enabled residential microgrid, interfaces with the rest of their system. We allow this to be dispatched, and so the utility can negotiate and indicate to the PV system how much of this excess power, right now this is electricity that's above and beyond what the residential loads are requiring, how much of that is going to be injected back into the grid. And so this allows the operations of the grid to remain stable. So voltage control, frequency control, those ancillary services that are required in the utility grid, this now becomes controllable. This concept of being able to control the amount of power injected from the PV high pen scenario, it's similar to what we might call curtailment in the wind industry, where we have some availability of the solar resource, but we choose to limit its injection. But because the energy storage is at a community level, we're already meeting the requirements of the load. So this is the extra energy going back into the system. The extra energy that the utility today would say, no, we don't want to accept, and we don't want you to have that PV system. This gives them a way to manage it. And so from the utility's perspective, this is how we're making the photovoltaic concepts more manageable and integratable into their system. So that was, in a very brief presentation, a very slice of part of what my research lab is doing to debunk some of the myths about a high penetration scenario. My research fits into the greater group of the power electronics and power systems, where we have 10 faculty supervising approximately 65 graduate students. We have 17 courses at the graduate level. We've got 3 new courses that we're developing at the graduate level, and 5 undergraduate courses. So this makes us one of the largest groups in the country for power systems. Our power group is part of the electrical and computer engineering department, which has 70 faculty, about 850 undergraduate students, and about 550 graduate students. Top 10 ranked program for electrical engineering, And the power is one of 7 focus groups in the department. As we scale up from the department to the college level, the department is one of many colleges. It's the flagship department for the college. Total engineering students, about 11,300, which represents 21% of the total university population, so extremely large university. That makes us the 3rd largest undergraduate engineering program in the country and the 8th largest graduate program. So that's on the teaching side. On the research side, we have the Texas Engineering Experiment Station. So when I'm in the classroom, I'm a A&M employee. When I'm in the research lab, I'm a TEAS employee. And it's one of the largest organizations for sponsored research in the country. So all of my projects run through there, $140 million in sponsored research last fiscal year. And if you happen to catch a A&M football game, if you happen to watch the Cotton Bowl, you probably saw images of this PV array. You probably saw images of my students installing it. And that's part of how we use the system in a unique partnership with the athletics department and our community outreach, as well as our research and teaching. So with that, thank you very much.
All right, great. Same deal on questions. And while anybody may or may not be raising their hand, I'd like to ask about this distributed storage or community-based storage. Would that be as detailed as an individual home having its own storage, or are you thinking more because the utility wants to have more control, it needs to be fewer locations of storage throughout the area?
So your question is actually a very loaded question because there's a couple of issues there. My concept is that it's not at the residential level for a couple of reasons. Is that as we look to move photovoltaic from a niche market to a full commodity, we have to take the expert factor out of that. This needs to become an energy appliance. So just as you would buy a refrigerator, you make the same kind of purchasing decision to buy PV. Having energy storage at a residential level necessarily means there's a preventive maintenance cycle in that, so batteries only last 3 to 5 years. So that means that you're adding not just first costs to the system, but reoccurring operational costs. So putting this at a small community level means that there's a new business model that can be developed. Whether this is a system aggregator who manages that community or a different service provider that manages that battery, that becomes a separate issue. So the residential homeowner need not worry about the effectiveness or the aging of the storage.
Question right here?
Yeah, Jeff Rinkemeyer, Iberdrola Renewables, and I'm kind of like you, spending a lot of my time these days debunking myths about renewable energy. And I think you stole my thunder on the first one. I was going to ask who actually would own the asset of the community storage, whether it be utility or third-party aggregator. I think that'll be an interesting business model. But the other one, you were talking about the level of penetration of solar energy in Germany, and I think in an earlier presentation we had heard that Germany's solar resource is about the same as Alaska, which would be the worst state in the U.S. for solar resource. With those two things in mind, what is the cost of Germany's wholesale power done? After it, and if you don't, I'll answer it if you don't know. But if you don't, it's actually gone down. Since the high solar penetration. Even in a state that's about as bad as Alaska. So.
Yeah. Well, I think that's an example of where the political will spawned the industry. And now with the reductions that you saw in the wholesale pricing, we actually see that it has become sustainable on its own. And that's really the key behind photovoltaics. It's not really the cells anymore. The cells are good enough. It's the balance of system. That's where the costs are. It's the installation costs. Labor rates continue to rise while commodity pricing continues to go down. And any kind of a system design that depends on reoccurring maintenance is something that is going to be incurring substantially more costs going forward. So if we view solar as not a technology, but as an energy appliance that's got a 25 to 30 year lifetime, we make that decision once, it's a turnkey project, and we're done. And by moving the storage into something that could become a new business model, we allow new economies to develop. That could be a service industry for that. It could be purchased and owned by the utility. And I think a lot of those questions are yet to be determined. But we see from the example simulations and data analysis that that certainly takes us into the right direction for achieving higher penetration.
All right, great. Another question? All right, thank you.
Thank you.